Welcome back. We are on level 4 of CryptoZombies. We're exploring the blockchain technology Solidity to understand how Web3 is going to impact the intersection of voice technology and blockchain, Web3, cryptocurrencies. We're exploring that intersection. Let's get started with level 4, Zombie Battle System. The time has come, human. Time to make your zombies fight. But zombie battles aren't for the faint of heart. In this lesson, we're going to be putting together a lot of the concepts you've learned in previous chapters. We're also going to learn about payable functions and how to build dApps that accepts money from players. Cool. We've got 13 chapters here in this lesson. Let's get started with chapter 1, payable. Up until now, we've covered quite a few function modifiers. It can be difficult to try to remember everything, so let's run through a quick review. 1. We have visibility modifiers that control when and where the function can be called from. Private means it's only callable from other functions within the same contract. Internal is just like private, but it can also be called by contracts that inherit from this one. And external can only be called outside the contract. And finally, public can be called anywhere, both internally and externally. Number 2, we also have state modifiers, which tell us how the function interacts with the blockchain. View tells us that by running the function, no data will be saved or changed. Pure tells us that not only does the function not save any data to the blockchain, but it also doesn't read any data from the blockchain. Both of these don't cost any gas to call if they're called externally from outside the contract, but they do cost gas if called internally by some other function. Then we have custom modifiers, which we learned about in lesson 3. Only owner and above level, for example. For these, we can define custom logic to determine how they affect a function. These modifiers can all be stacked together on a function definition as follows. We've got a function, name of a function, external modifier, view modifier, only owner, and then additional modifiers can get stacked. In this chapter, we're going to introduce one more function modifier, payable. The payable modifier. Payable functions are part of what makes Solidity and Ethereum so cool. They are a special type of function that can receive Ether. Let that sink in for a moment. When you call an API function on a normal web server, you can't send US dollars along with your function call, nor can you send Bitcoin. But in Ethereum, because both the money, Ether, and the data, the transaction payload, and the contract code itself all live on Ethereum, it's possible for you to call a function and pay money to the contract at the same time. This allows for some really interesting logic, like requiring a certain payment to the contract in order to execute a function. Let's look at an example. Online store function buy something is external, so it can only be called outside of the contract, and payable, which I guess allows you to send Ether. Let's check to make sure Ether was sent to the function call, message.value equals 0.01 Ether. If so, some logic to transfer the digital item to the caller of the function. Transfer the thing, message.sender. Here, message.value is a way to see how much Ether was sent to the contract, and Ether is a built-in unit. What happened here is that someone would call the function from Web3.js from the dApp's JavaScript front end as follows. Assuming online store points to your contract, buy something, we say from web3.eth.default account, which I guess is going to grab the default account of whoever signed in, and then the value web3.utils.toWe. I don't know what this toWe means, and then this 0.01 matches the amount of Ether we are expecting. Notice the value field where the JavaScript function specifies how much Ether to send, in this case 0.001. If you think of the transaction like an envelope, and the parameters you send to the function call are the contents of the letter you put inside, then adding a value is like putting cash inside the envelope. the letter and the money get delivered together to the recipient. Note, if a function is not marked payable and you try to send Ether to it as above, the function will reject your transaction. Putting it to the test. Let's create a payable function in our zombie game. Let's say our game has a feature where users can pay ETH to level up their zombies. The ETH will get stored in the contract which you own. This is a simple example of how you can make money on your own games. Alright, so number one, let's define a uint named level up fee and set it equal to 0.001 Ether. Create a function named level up. It will take one parameter, zombie ID, a uint. It should be both external and payable. The function should first require that message.value is equal to level up fee. It should then increment the zombie's level, zombie ID dot level plus plus. Seems pretty straightforward. The only question I have here is about point 2 up top. We're talking about the cost to execute functions with gas, and if it's pure or view and it's called externally from outside of the contract, it's free. But if it's called inside the contract, it still costs gas. My question is this strictly for Ethereum, or is this true of any smart contract that is published using the Solidity programming language? So is this a feature of the technology of Ethereum, or is this a feature of the programming language Solidity? Like if I go over to Polygon or Loom or to some other decentralized computing platform that I can write smart contracts on, will the same rules apply for them being free? That's the question I have, but let's keep moving. Define a uint called level up fee. Set it equal to 0.001 Ether. Uint level up fee equals 0.001 Ether. Okay. Create a function named level up. So we want a function called level up, and it has parameters, only one, and it is a uint of underscore zombie ID. It is external payable function. The function should first require that msg.value equals level up fee. It should then increment the zombies level, so we say zombies of underscore zombie ID dot level plus plus. We got it, first try. Chapter 2, withdrawals. In the previous chapter we learned how to send Ether to a contract. So what happens after you send it? Great question. After you send Ether to a contract, it gets stored in the contract's Ethereum account, and it will be trapped there unless you add a function to withdraw the Ether from the contract. You can write a function to withdraw Ether from the contract as follows. Get paid is ownable, function withdraw, external only owner, address, payable, owner equals address uint 160 of owner. So this is the owner's address, and then we say owner transfer address this dot balance. So we transfer the balance to the owner. Note that we're using owner and only owner from the ownable contract, assuming that was imported. And most important for owner variable, that it's have to be a address payable type for doing a sending and transferring Ether instruction. But our owner isn't a type address payable, so we have to explicitly cast to address payable. Casting an integer type like uint 160 to address produces an address payable. You can transfer Ether to an address using the transfer function, and address this dot balance will return the total balance stored on the contract. So if 100 users had paid 1 Ether to our contract, address this dot balance would equal 100 ether. You can use transfer to send funds to any Ethereum address. For example, you could have a function that transfers ether back to the message.sender if you overpaid them. uint item fee equals 0.001 ether, message.sender.transfer, message value minus item fee. So however much they sent minus the fee is how much we send back to them. Or in a contract with a buyer and a seller, you could save the seller's address in storage. Then when someone purchases his item, transfer him the fee paid by the buyer. Seller.transfer, message.value. These are some examples of what makes Ethereum programming really cool. You can have decentralized marketplaces like this that aren't controlled by anyone. Putting it to the test. 1. Create a withdrawal function in our contract, which could be identical to the get paid example above. The price of Ether has gone up over 10x in the past year, so while 0.001 is about $1 at time of writing, if it goes up 10x again, 0.001 Ether will be $10 and our game will be a lot more expensive. So it's a good idea to create a function that allows us, as the owner of the contract, to set the level up fee. Create a function called setLevelUpFee that takes one argument. uint fee is external and uses the modifier only owner. The function should set levelUpFee equal to _ fee. Okay, so we're going to want this function to be copied. We want to create this withdrawal function. The price of Ether has gone up, so it goes up again. A lot more expensive. Set the level up fee. Let's create a function called setLevelUpFee. Function setLevelUpFee. A uint of _fee. External can only be called outside of our function, and only the owner can call it. Within this function, we set level up fee equal to _fee, which is going to write to the blockchain. Address payable owner, and then we get our own owner function. Zombie feeding is zombie factory is ownable and ownable. We have an _ownable. Do we have an owner function? We do have an owner function. Okay. Looking good. Let's send it, see what happens. We got it. It is really cool to be able to send payments directly inside of a programming language. Typically right now we use Stripe, which is an awesome technology. However, it takes a lot to import Stripe, get an API key, set up transactions inside of our code base. So to have the payable keyword allows us to accept Ether payments for API calls. Pay bit fee. It's pretty cool. Chapter 3, Zombie Battles. Now that we've learned about payable functions and contract balances, it's time to add functionality for zombie battles. Following the format from previous chapters, we'll organize our code by creating a new file contract so each file is also a contract, for the attack functionality that imports from the previous contract. Let's review creating a new contract. Repetition leads to mastery. I like that. Repetition leads to mastery. Repetition leads to mastery. I agree 100%. Following the principle of Kaizen, getting 1% better each day, repeating every day gets us there. If you can't remember the syntax for doing these, check out Zombie Helper Soul for the syntax, but try to do it without peeking to test your knowledge. Okay. So the first thing we want to do is use the Solidity version of this. So I think it's Solidity. We'll just set that and see if that's right. And then we want to import zombie helper.soul, and we'll need that inside of quotes. Declare a new contract zombie attack is zombie helper. Let's see if I did that right. I did something wrong. Pragma Solidity. I don't know what the word pragma means. Let's see what the word pragma means. A directive or pragma is a language construct that specifies how a compiler should process its input. Okay. Chapter 4, Random Numbers. Great, now let's figure out the battle logic. All good games require some level of randomness, so how do we generate random numbers in Solidity? The real answer here is you can't. Well, at least you can't do it safely. Let's look at why. Random number generation via KeySack256. The best source of randomness we have in Solidity is the KeySack256 hash function. We could do something like the following to generate a random number. Generate a random number between 1 and 100. Random nonce equals 0. Random equals uint casting of KeySack256 hash. ABI.encode pact of now, which is the current time. Message sender. Random nonce, and then modulo 100. Random nonce plus plus, so now it's 1, and then we get a random 2. Uint casted of KeySack256 hash. ABI.encode pact to encode the string of the now timestamp message sender in rand nonce. What this would do is take the timestamp of now, the message sender, and an incrementing nonce, a number that is only ever used once, so we don't run the same hash function with the same input parameters twice. We could then pack the inputs and use KeySack to convert them to a random hash. Next, it would convert that hash to a uint and then use modulo 100 to take only the last 2 digits. This will give us a totally random number between 0 and 99. However, this method is vulnerable to attack by a dishonest node. In an Ethereum, when you call a function in a contract, you broadcast it to a node or nodes on a network as a transaction. The nodes on the network then collect a bunch of transactions, try to be the first to solve a computationally intensive mathematical problem as a proof of work, and then publish that group of transactions along with their proof of work as a block to the rest of the network. Once a node has solved the proof of work, the other nodes stop trying to solve the proof of work, verify that the other node's list of transactions are valid, and then accept the block and move on to trying to solve the next block. This makes our random number function exploitable. Let's say we had a coin flip contract. Heads, you double your money, tails, you lose everything. Let's say it used the above random function to determine heads or tails. Random is greater than or equal to 50 is heads, random less than 50 is tails. If I were running a node, I could publish a transaction only to my own node and not share it. I could then run the coin flip function to see if I won, and if I lost, choose not to include that transaction in the next block I'm solving. I could keep doing this indefinitely until I finally won the coin flip and solved the next block and profit. So how do we generate random numbers safely in Ethereum? Because the entire contract of the blockchain is visible to all participants, this is a hard problem, and its solution is beyond the scope of this tutorial. You can read this Stack Overflow thread for some ideas. One idea would be to use an oracle to access a random number function from outside of the Ethereum blockchain. I'm interested to learn more about oracles. Of course, since tens of thousands of Ethereum nodes on the network are competing to solve the next block, my odds of solving the next block are extremely low. It would take me a lot of time or computing resources to exploit this profitably, but if the reward were high enough, like if I could bet $100 million on the coin flip function, it would be worth it for me to attack. So while this random number generation is not secure on Ethereum, in practice, unless our random number function has a lot of money on the line, the users of your game likely won't have enough resources to attack it. Because we're just building a simple game for demo purposes in this tutorial and there's no real money on the line, we're going to accept the trade-offs of using a random number generator that is simple to implement, knowing that it isn't totally secure. In a future lesson, we may cover using oracles, a secure way to pull data from outside of Ethereum to generate secure random numbers from outside the blockchain. Put it to the test. Let's implement a random number function we can use to determine the outcome of our battles, even if it isn't totally secure from attack. Give our contract a uint called randomNonce and set it equal to 0. 2. Create a function called randmod, a random modulus. It will be an internal function that takes a uint named modulus and returns a uint. The function should first increment randomNonce. Finally, it should in one line of code calculate the uint typecast of the keysack256 hash of abi.encodePact, now, message sender, randomNonce, and return that value %_modulus. Woo, that was a mouthful. If you didn't follow, just take a look at the example above where we generated a random number. The logic is very similar. Step 1. Give our contract a uint called randNonce and set it equal to 0. Okay. Create a function called randmod. It will be an internal function that has one parameter of a uint of _modulus. It is an internal function and it returns a uint. The function should first increment randomNonce plus. Finally, it should in one line of code calculate the uint, return uint casted keysack 256 hash of abi.encode pact of now, which is a timestamp, message.sender, which is the Ethereum address of the person calling the function, and randomNonce, which is a number that we increment to make sure we never get the same number twice. Doing something wrong with the randomNonce. That looks fine. Uint casted keysack 256 abi.encode pact now, message.sender, randomNonce. Do we then need to modulo it? And return that value %modulus, okay. Modulus _modulus. That was it. I didn't read all the instructions. Chapter 5, Zombie Fightin'. Now that we have a source of some randomness in our contract, we can use it in our zombie battles to calculate the outcome. Our zombie battles will work as follows. You can choose one of your zombies and choose an opponent's zombie to attack. If you're the attacking zombie, you need to have a 70% chance of winning. The defending zombie will have a 30% chance of winning. All zombies attacking and defending will have a win count and a loss count that will increment depending on the outcome of the battle. If the attacking zombie wins, it levels up and spawns a new zombie. If it loses, nothing happens except its loss count incrementing. Whether it wins or loses, the attacking zombie's cooldown time will be triggered. There's a lot of logic to implement, so we'll do it in pieces over the coming chapters. Put it to the test. Give our contract a uint variable called attack victory probability and set it to 70. Create a function called attack. It will take two parameters, a uint of zombie ID and a uint of target ID. It should be an external function. Leave the function body empty for now. Okay, so now we want a uint called attack victory probability and set it equal to 70%. Then we want to create a new function called attack with two parameters, a uint called underscore zombie ID, which is the ID of the attacking zombie, and a uint of underscore target ID, which is the ID of the defending zombie, and it's an external function, which means it can only be called outside of our smart contract. That's it. Chapter 6, Refactoring Common Logic. Whoever calls our attack function, we want to make sure the user actually owns the zombie they're attacking with. It would be a security concern if you could attack with someone else's zombie. Can you think of how we could add a check to see if the person calling this function is the owner of the zombie ID they're passing in? Give it some thought and see if you can come up with the answer on your own. Take a moment. Refer to some of the past lessons code for ideas. Answer below. Don't continue until you've given it some thought. So I'll take a pause here. We want to make sure they're the user that actually owns the zombie they're attacking with. I think this could be solved in one of two ways. Either we can have a return statement that will enforce a check and throw an error if it happens, or a function modifier that will check the zombie owner before the function is actually called. Either case, we're going to be having a require in there, so I guess we would want it to be a function modifier if we're going to reuse this function, reuse the modifier on multiple functions. But if we're only going to be checking once whether the user actually owns a zombie they're attacking with, then we just want to implement that require in one line in our function. And we would check it by just inside of our require, we would say require zombie to owner of the zombie's ID equals message.sender. So then we're checking that the owner ID, the owner's Ethereum address, is equal to the owner of the zombie's Ethereum address is equal to the Ethereum address calling the function. The answer. We've done this check multiple times now in previous lessons. In change name, change DNA, and feed and multiply, we use the following check. Require message.sender double equals zombie to owner zombie ID. There's the same logic we'll use for our attack function. Since we're using the same logic multiple times, let's move it into its own modifier to clean up our code and avoid repeating ourselves. This follows the dry principle of clean code. Dry, shout out to Ian Fua, who reminded our team of it. Dry code means don't repeat yourself. So it reduces repetition of software patterns, replacing it with abstractions or using data normalization to avoid redundancy. Yeah, so this makes sense. So let's declare our modifier. Put it to the test. We're back to zombiefeeding.sol. Since this is the first place we use that logic, let's refactor it into its own modifier. Create a modifier called owner of. It will take one argument, zombie ID, which is a uint. The body should require it that message.sender is equal to zombie to owner of zombie ID, then continue with the function. You can refer to zombiehelper.sol if you don't remember the syntax for a modifier. Change the function definition of feed and multiply such that it uses the modifier owner of. Now that we're using a modifier, you can remove the line require message.sender equals zombie owner of zombie ID. Seems pretty straightforward. Step 1, create a modifier. Where do you want me to put it? Right here. Okay, modifier, owner of, and then it will have a uint of underscore zombie ID. The body should be a require that msg dot sender equals zombie to owner of underscore zombie ID. Then continue the function, which is just underscore semicolon. Okay, create a modifier, did that. Owner of, did that. One argument zombie ID uint, did that. The body should require, we got the require message.sender, we have that equal to zombie owner, zombie to owner underscore zombie ID. Then continue with the function, continue with the function. Okay, number 2, change the function definition of feed and multiply such that it uses the modifier owner of. Feed and multiply. We then add this function modifier owner of underscore zombie ID. Did number 2, change the function definition, and then we can remove the line of this require because we're already doing it. We don't need to duplicate it. Got it. Okay, we're over halfway through. Chapter 7, more refactoring. We have a couple more places in zombiehelper.sol where we need to implement our new modifier owner of. Put it to the test. Update change name to use owner of. Change name. Boop, boop, boop. Delete that. Now we say owner of, and then we pass in underscore zombie ID. Okay, so we did change name. Now we need change DNA. Change DNA. We'll also do owner of, pass in the underscore zombie ID, and then we remove this require. We just removed a few lines of code, changed some function definitions. Chapter 8, back to attack. Enough refactoring, back to zombieattack.sol. We're going to continue defining our attack function now that we have the owner of modifier to use. Put it to the test. Add the owner of modifier to attack to make sure the caller owns zombie ID. The first thing our function should do is get a storage pointer, which means that it's coming straight from the blockchain, to both zombies so we can more easily interact with them. Declare a zombie storage named myZombie and set it equal to zombie ID, and then declare a zombie storage named enemyZombie and set it equal to enemyZombies underscore target ID. Step 3, we're going to use a random number between 0 to 99 to determine the outcome of our battle. So declare a uint called rand and set it equal to the result of rand mod function with 100 as an argument. Okay, step 1, add owner of to attack. So to attack, we add the modifier owner of and pass in underscore zombie ID. We've now done step number 1. First thing our function should do is get a storage pointer to both zombies. So we want to declare a zombie variable from storage called myZombie and set it equal to zombies underscore zombie ID. Now we're going to want to do the same thing for the enemy zombie, zombie storage enemy zombie is going to be equal to zombies underscore target ID. We're going to use the random number between 0 to 99 to determine the outcome. So now we want a uint called rand, which equals random modulus of 100, which should give us a random number between 0 and 99. Chapter 9, Zombie Wins and Losses. For our zombie game, we're going to want to keep track of how many battles our zombies have won and lost. That way we can maintain a zombie leaderboard in our game state. You could store this data in a number of ways in our DApp, as individual mappings, as a leaderboard struct, or in the zombie struct itself. Each has its own benefits and trade-offs depending on how we intend on interacting with the data. In this tutorial, we're going to store the stats on our zombie struct for simplicity and call them win count and loss count. So let's jump back to zombiefactory.sol and add these properties to our zombie contract. Put it to the test. Step 1, modify our zombie struct to have 2 more properties, win count and loss count. Both are uint 16s. Remember, since we can pack uints inside structs, we want to use the smallest uints we can get away with. A uint 8 is too small with only 256 values. If our zombies attacked once per day, they could overflow this within a year, but 2 to the 16th is 65,536. So unless a user wins and loses every day for 179 years straight, we should be safe. Now that we have new properties on our zombie struct, we need to change our function definition and create zombie. Change the zombie creation definition so it creates each new zombie with 0 wins and 0 losses. Step 1, modify the zombie struct to have win count and lose count. Uint of win count, and then a uint, and we want it to be uint 16. Loss count. Got it? Okay, now we have new properties. We can change create zombie. So we've got name, DNA, level, ready time. Now we want to add comma, win count. Win count is going to be equal to 0, and then loss count is also going to be equal to 0. Zombie victory. Now that we have a win count and a loss count, we can update them depending on which zombie wins the fight. In Chapter 6, we calculated a random number from 0 to 100. Now let's use that number to determine who wins the fight and update our stats accordingly. Put it to the test. Step 1. Create an if statement that checks if rand is less than or equal to attack victory probability. If this condition is true, our zombie wins, so increment the zombie's win count, increment the level, increment the enemy's loss count, run feed and multiply function, check zombie feeding.sol to see the syntax for it. For the third argument species, pass the string of zombie. It doesn't actually do anything at the moment, but later we could add extra functionality for spawning zombie-based zombies if we wanted to. Okay, this doesn't zombie victory. I guess chapter 11 will probably do defeat. So let's start on level. Step 1, create an if statement that checks if rand is less than or equal to attack victory probability. If the condition is true, we want to say my zombie dot win count plus plus, writing to the blockchain, my zombie dot level plus plus, also writes to the blockchain, enemy zombie dot loss count plus plus, they lose, also writes to the blockchain. Then after that we run the feed and multiply function. Does zombie helper extend something else? It does. Great. Feed and multiply. We need a zombie ID, a target DNA, and then species. Zombie ID is the first argument. We have that of underscore zombie ID. Then we need a target DNA. We have a DNA for a zombie, so the target DNA is going to be underscore enemy target ID. No, not target ID. We want enemy zombie. Enemy zombie dot DNA. And then for the third argument, we want to pass in zombie. This should feed and multiply with our zombie ID being our zombie that won, the target DNA being the DNA of the defeated zombie, and the species of the thing we're feeding on is a zombie. We did something wrong. Feed and multiply zombie ID, enemy zombie.dna, and zombie. Okay, so we did something wrong here. Feed and multiply function. Check zombie feeding.sol. Okay, we need a uint, and a string. We have a uint. Enemy zombie is a zombie. And zombies have a uint of DNA. And then we have a string of species. Let's check these. Okay. Create an if that checks if rand is less than or equal to attack victory probability. The condition is true. Zombie wins. My zombie's win count is incremented. My zombie's level is incremented. Enemy zombie loss count. Loss count is incremented. And then we run the feed and multiply function. For the third argument, pass the string zombie. Confused what I did wrong. What are we doing wrong here? Seems we're doing something wrong on this line. But what is it that's incorrect? I misspelled feed and multiply. I misspelled the function name. Okay. We did everything right. Zombie loss. Now that we've coded what happens when your zombie wins, let's figure out what happens when it loses. In our game, when the zombies lose, they don't level down. They simply add a loss to their lose count, and their cooldown is triggered, so they have to wait a day before attacking again. To implement this logic, we'll need an else statement. Else statements are written just like in JavaScript. Great. Put it to the test. Add an else statement if our zombie loses. Increment my zombie's loss count, increment enemy zombie's win count, and then run the trigger cooldown function on my zombie. This way the zombie can only attack once per day. Remember, trigger cooldown is already run inside feed and multiply, so the zombie's cooldown will be triggered whether he wins or loses. Got it. Okay, so now we want an else statement. Inside of the else statement, so our zombie is lost here. My zombie dot loss count plus plus enemy zombie dot win count plus plus, and then finally we want the trigger. Where's trigger cooldown? Trigger cooldown, and we just want to pass in a zombie object. Trigger cooldown for my zombie. Chapter 12, wrapping it up. Congratulations, this concludes Lesson 4. Go ahead and test out your battle function to the right. Claim your reward. After winning the battle, your zombie will level up. Your zombie will increase his win count. You will spawn another zombie to add to your army. Go ahead and try the battle, then proceed to the next chapter. No. Cool. Congrats, you've completed level 4. We've been upgraded. We've added a new level 1 zombie. Show off your zombie army to your friends. I wonder where this takes me to. Payable functions is what we learned about today. We learned about withdrawing ETH from smart contracts. Random number generation, and more. Cool. If you've got any questions, please ask. Ask away on any social media platform at Voice First AI. Hope you got some value out of this, learning about blockchain development on Solidity for Ethereum. And enjoy the rest of your day. Thanks, everyone.